In this video, we are going to do some more examples on the substitution method with regard to integrals. So let's see this example, the integral of 2 over 3z plus 1 dz. Using the substitution, we want to do this integral. As with other examples, I suggest that you pause the video and try to do this on your own before continuing with the solution or before continuing with watching the solution. So let's see which substitution is the best one to solve this problem. Let u be the new variable, u be 3z plus 1. The derivative of u with respect to z is 3. Or if I solve for dz, it's going to be du over 3. To clarify this, cross multiplication gives us 3dz equals du, or du equals 3 times dz. So far I know that this denominator is the new variable u, and I want to know that what is dz in terms of du. Here, if I divide both sides by 3, dz is going to be du over 3. So this is du over 3. So let's see what we have so far. The integral of 2 over u du over 3. 2 and 3 are constants, can be pulled out of the integral, 2/3. And I have integral of 1 over u du. I know that what is the antiderivative of 1 over u, or 1 over the variable. That is ln of absolute value of the variable. So ln of absolute value of u. And then plus c at the end, because it's an indefinite integral. Just it remains to do the back substitution. Since it's an indefinite integral, we need to go back to the original variable of the question, which was the original variable was z. So I need to respond to this question in terms of z. U is 3z plus 1, so the final answer is going to be 2/3 ln of absolute value of 3z plus 1 and then plus c. That's the answer that we are going to type in here, 2/3 ln of absolute value of 3z plus 1 and then at the end plus c. Let me do another example. I want to find the integral of secant squared of 10t dt. Just as a reminder, the derivative of, let me just make a reminder here from Calc 1. As you might remember, the derivative of tangent of x using the quotient rule, because tangent is tangent is sine over cosine. And using the quotient rule, the derivative of tangent is secant squared of x. So if I want to write this down in terms of integrals, it says that the integral of secant squared of x is going to be tangent of x and at the end plus c. But here I don't have secant squared of just the variable. It is 10 times the variable, 10t. So can you guess that what substitution we should use here? We'll let u be what? U is going to be 10t. So I want to make this 10t as the new variable u. Now the derivative of u with respect to t is 10. Cross multiplication gives me du is 10 dt. And here, if I want to write dt in terms of du, in this equation, I need to divide both sides by 10. So that dt is du over 10. So let's continue with this integral of secant squared of u du over 10. Over 10 is like 1/10 has been multiplied by the function, and since it's a constant has been multiplied by the function, that 1/10 can be pulled out of the integral. So secant squared of u du, which equals 1/10. Antiderivative of secant squared is, as by that reminder, is tangent of u plus c. Just it remains to do the back substitution. U is 10t, so it's going to be 110. Tangent of 10t plus c. So that's the answer that we need to type in here. 110 tangent of 10t and then plus c. Let me give an example of the substitution just as a practice for the definite integrals. Again, my suggestion is to pause the video and try to solve this integral using substitution on your own and come up with the value that should be typed in this space. So under the radical, I have x squared minus 16. So a good substitution for this problem is going to be, we let u be what? Under the radical, x squared minus 16. Under the radical, we have x squared minus 16. To try to simplify this problem, we let u be x squared minus 16. And soon we'll see that that's a very good substitution. In fact, the derivative of u with respect to x is 2x. The cross multiplication tells me that du is 2x dx. So let's see what we have so far. Under the radical is just u. And I need to think about x dx. In the last equation inside the rectangle, I have du is 2x dx. That we have an extra 2. So if I divide both sides by 2, I can get rid of that extra 2. So x dx is du over 2. So that's going to be du over 2. So let me rewrite the integral in terms of the new variable u, radical u du over 2. This is a definite integral. We don't, after integration, we don't need to go back to the original variable. But be careful here. I need to change the limits of the integral according to the substitution. The substitution is, let me focus on that. The substitution is u is x squared minus 16. So when I have the lower limit of the integral, when I have 4, when x is 4, u is what? U is going to be 4 squared minus 16. So 4 squared is 16. 16 minus 16 is going to be 0. So the lower limit of the integral will be 0. What about the upper limit of the integral? 5. So when x is 5, the corresponding value for u is 5 squared minus 16. 5 squared is 25 minus 16 gives me 9. So it's going to be 9. This 1/2 or du over 2, which has a 1/2, that 1/2 comes out. 1/2 the integral from 0 to 9 of radical u du. We have done the integral of the radical of the variable before, and that in fact you have seen that in Calc 1, and we in the earlier videos we had a reminder of that. So antiderivative of radical u is 2/3 u to the power of 3/2. And this should be evaluated at, let me rewrite that. So 1/2 is there. Antiderivative of radical u is 2/3 u to the power of 3/2. Just as a reminder, we rewrite radical u as u to the power of 1/2 and use the power rule. And it should be evaluated at these numbers, and then we do the subtraction. Before doing that, I see that 2 and 2 cancel out. Now, 1/3 u to the power of 3/2, I should evaluate at 9, so 1/3 9 to the power of 3/2. So this function, in fact, evaluated at 9, minus this function at 0, minus 1/3 times 0 to the power of 3/2. 0 to any positive power is going to be 0, so the second term is nothing except 0. It remains to simplify this. 1/3 times 9 to the power of 3/2. 9 to the power of 3/2 is 27. Why? Because 9 to the power of 1/2 is like radical 9 is 3, and 3 cubed is 27. Using basic algebra information, 9 to the power of 3/2 is 27. And 1/3 times 27 is going to be 9. So the value of this integral is equal to 9. Another example. The integral from pi over 6 to pi over 3 cosine x over sine cubed x dx equals to what? I want the value of this integral. What substitution do you suggest? What do you think that it's the best way to simplify this integral using a good substitution? Keep in mind that the derivative of sine is cosine. And I see that at the bottom I have sine cubed, and on the top there is one cosine. So a very good substitution here is going to be u equals sine x. First, let's see how is the u is related to dx. The derivative of u with respect to x, the derivative of sine x is cosine x. Cross multiplication tells me that du is cosine x dx. So, first of all, u is sine x, so this denominator is u cubed. And du is cos x dx. In fact, I have cos x dx is du. So you see that the substitution makes the problem much easier. So this is going to be the integral of 1 over u cubed du. One important thing is to change the limits of the integral according to substitution. So what's the substitution? The substitution is u equals sine x. Let's see how it affects the limits of the integral. So u is sine x. When x is pi over 6, from pre-calculus, what was the sine of pi over 6? It is 1/2. And when x is the upper limit of the integral, pi over 3, sine of pi over 3 is radical 3 over 2. So the limits of the integral, they change according to substitution. The lower limit of the integral is 1/2. The upper limit of the integral is radical 3 over 2. So now first I need to find antiderivative of 1 over u cubed. To use the power rule, I need to rewrite 1 over u cubed as u to what power? Minus 3. Using basic algebra, we know that 1 over u cubed equals u to the power of minus 3. And the reason that I write it u to minus 3 is because I want to use the power rule. If u was in the denominator, I couldn't use the power rule. It should be on the top. So let me continue next page. So what we have so far we had the integral from 1/2 to radical 3 over 2 of u to the power of minus 3 du. Using the power rule, antiderivative of u to minus 3 is u to minus 3 plus 1, which is minus 2 over minus 2. And then we need to evaluate at these numbers. Before the evaluation, let's write this without negative exponents. So I have 1 over minus 2 here, minus 1/2. And u to the power of minus 2 when moved to the denominator becomes u squared at the bottom. So I can write the whole thing as minus 1 over 2u squared. So these two are the same thing. Okay, now I need to evaluate these at these numbers at the limits of the integral and do the subtraction. The evaluation of this function at the upper limit, minus 1 over 2 times what squared? Radical 3 over 2 squared. Minus the evaluation of this number, of this function at 1/2. Minus 1 over 2 times 1/2 squared. The first term didn't really need the parentheses, but let me put parentheses for more clarification. So I evaluated minus 1 over 2u squared as radical 3 over 2. That's the first parentheses. And minus the evaluation of that function at 1/2, which is the second parentheses. So the first term is going to be 1 minus 1 over 2 times radical 3 over 2 squared. Radical 3 squared is 3, 2 squared is 4. So 2 times 3/4 minus minus here becomes a plus. 1 over 2 times 1/2 squared is 1/4. So in the first fraction, the denominator, 2 and 4 can be simplified as a 2 here. In the second one, the same thing. So the first fraction minus 1 over 3/2, which is the same as minus 2/3. And the second fraction plus 1 over 1/2. 1 over 1/2 is the same as 2. Again, the first fraction here, minus 1 over 3/2. 1 over 3/2 is the 2/3. So that's why the first term is minus 2/3. And the second fraction, 1 over 1/2. 1 over 1/2 is 2. So this fraction is going to be 2. And minus 2/3 plus 2 is going to be 4/3. And that's the final answer for this integral. So let me go back and write the answer inside this box. So part of the solution to this example was on this page, and the other part is here.